Welcome to Econ 317. In this instruction video, we will go over the definition of a derivative. So we want to define derivative of a function y equal to f of x at a point x in the domain. The function y is a function of real variable, and so we will write down first the formal definition for y equal to f of x at x equal to some particular value of some particular point in the domain. I'll name it x0. The derivative, the notation for the derivative first is dy over dx. We read it as dy over dx is the limit when h tends to 0 of the function value at x0 plus h is a small number, goes to 0 in the limit, minus the function value at x0. I divide this difference by h and I compute this limit. If this limit exists, we'll say that is the derivative of the function y equal to f of x at x equal to x0. So first let's do an example of the computation of the derivative. So first I will take one example. Let me say y is equal to x square, which means f of x is x square, and I want to compute the derivative at point x0. So let's go now to the definition. The derivative dy over dx is equal to the function value at x0 plus h, so which is x0 plus h whole square minus the function value at x0, so x0 square. I divide it by h and I take the limit h going to 0. So that's the definition. We can do some algebra. We know the square x0 plus h. I will write down the expression for this. So it is equal to h0 going to h going to 0, x0 square plus h square plus 2x0 times h. This is the value of x0 plus h whole square minus x0 square, and I divide it by h. This is what we want to compute, and so I will do some simplification. We can see we can cancel out one term, x0 square. So what remains is limit h going to 0, h square plus 2x0h, and I divide by h. Now we can factor out h from the first from the terms in the numerator. So limit h going to 0, h times, so it was h square, I will remain only h will remain. So I obtain h in the first term, then 2x0 multiplied by h. I have factored out h, so what remains is 2x0, and I am dividing it by h. Remember, here h is not 0, h is tending to 0. That's how we are able to define the quotient because h is not a 0. But then I can cancel out h and h from both numerator and denominator. What remains is limit h going to 0, h plus 2x0. And now we can apply the limit. H is going to 0, so this whole expression becomes 2x0. In other words, I have obtained the derivative. So for y equal to f of x, which is x square, what we have obtained is dy over dx being equal to 2x. I am writing it at general form without resorting to x0 because we can pick any value of x and obtain the derivative at that point. So let's take some examples. For x0 equal to 1, the derivative dy over dx 2 times 1 turns out to be 2. If I take x0 to be 2, I can do the same computation for x0 equal to 2. The derivative dy over dx is 2 times x0, which is 2 now. So 2 times 2 turns out to be 4. So this is the way we compute the derivative. I will also like to show you the notion of derivative using geometry. So we can have a geometrical interpretation. Let me draw this graph. I have y on the vertical, x on the horizontal. And so this y equal to x square is the graph of the parabola. I will draw only the one which is on the positive axis, positive values of x0. And so one geometrical interpretation for the derivative is that it is the slope of the tangent drawn at any given point on the graph of the function y equal to f of x. So let me draw a tangent. We know the definition of the tangent. It is the straight line which hits the graph exactly at that point. So if x0 is 1, I have drawn the tangent. Slope of this tangent is the derivative at x0 equal to 1. I will like to draw at least one more tangent to show how derivative change as we go from one point to the other on the graph. So now I have the derivative, let's say at x0 equal to 2, and you can see the tangent has steeper slope, and that's the derivative. So this is the geometrical interpretation of the derivative. And now I will give some first a general formula for the derivative of functions of this class. So instead of writing y equal to x square, I can write a general functional form. Y equal to x to the power n, where n is a real number which can be any real number, positive, negative, fraction, or irrational number, and the same formula will work. The derivative of y with respect to x is n times x to the power n minus 1. So let's look at some examples. Y equal to x to the power 3. The derivative dy over dx is 3 times x to the power 3 minus 1 turns out to be 3x squared. Maybe I take another example, y equal to x to the power 1 half. As I have already claimed, the formula works for every real number, so this is a fraction. The derivative dy over dx is 1 half x to the power 1 half minus 1. So 1 half x to the power minus half. We could also write it as, I can take the power, negative power in the denominator. Can write it as 1 over 2 x to the power half. We can also use the notation of the square root, and it's the same expression. Maybe I have not yet taken an example of a negative number, so let's take first example of a negative whole number. So for y equal to x to the power minus 1, dy over dx is equal to minus 1 x to the power minus 1 minus 1. So this turns out to be minus 1 x to the power minus 2. I can take the negative power in the denominator and I can write it as x squared. Another example where I take a negative number, but this time a fraction. So let's have y equal to x to the power minus 3 over 2. This takes me to the derivative dy over dx becoming minus 3 half. So the exponent becomes the coefficient and I reduce the exponent by 1. So what we have obtained, minus 3 over 2 x to the power minus 5 over 2. I can take the negative power to the denominator. I can write it as minus 3 over 2 x to the power 5 over 2. Maybe I can write it down as using the square root symbol, 2 square root of x to the power 5. These are all equivalent expressions. The formula works not only for whole numbers and rational numbers, it works even for irrational numbers. So let me write y equal to x to the power square root 2. We have seen before, square root 2 is an irrational number, but the derivative dy over dx is the same formula. So this coefficient, the index, the power becomes the coefficient, and then I reduce the power by 1. So that will be the derivative of y equal to x to the power half, x to the power square root 2. And this is a good point to stop.